So in this video, we are talking about symmetric matrices. So when do we call a matrix to be a symmetric matrix? When the transpose of the matrix equals the matrix itself. Now notice this, that in order for A to equal its transpose, we must have A as a square matrix, right? So A must be a square matrix. All right. Okay. Now, so let's take up a couple of examples. For instance, if I look at a matrix here, I'm just writing it, just randomly. All right. And you look at its transpose, meaning change rows to columns and columns to rows. You can see right here that these two do not agree, right? So in this case, this matrix is not a symmetric matrix. Okay. So on the other hand, let's take up another matrix of the same kind. That is, let's say we have 2 1. Now we know that in order for this to be symmetric, I have to have these two identical. Doesn't matter what that is. So if I look at the transpose here, these are the same. Okay. So there is one particular feature of symmetric matrix that we are going to consider in this lecture or presentation, that it is diagonalizability. All right. Now remember this, that you had seen that for a square matrix to be diagonalizable, that is, in order for that to be similar to a diagonal matrix, okay, we must have, so if the dimension of the matrix are n by n, okay, then we must have n linearly independent eigenvectors. Okay. And in this case, like when we have the matrix that we have, or for a symmetric matrix A, we have many good properties that we already have, which will help the diagonalization not only possible, but they will also make it much nicer. So for a symmetric matrix, we can always diagonalize it. Okay, diagonalize it orthogonally. Okay, that means that we would be able to find, i.e., we can find an orthogonal matrix. Remember what is an orthogonal matrix? An orthogonal matrix is a matrix whose columns are orthonormal vectors. Okay, so an orthogonal matrix P such that what here we have our matrix in the under discussion as what? A. So what this means is that we will have this equal to D, where D is an orthogonal matrix, and I'm sorry, where D is a diagonal matrix and P is an orthogonal matrix. Okay. All right. So let's take up an example from the book, because if I just make up an example from out of my head, it may not have good numbers. Okay, so here we go. So we are looking at this matrix: 5, -4, -2, -4, 5, 2, -2, 2, 2, right? So, so let's try to orthogonally diagonalize this matrix. Okay, so if we go for it, that is for its eigenvalues and eigenvectors, what you will notice is that it has two eigenvalues. One is repeated of, and it is of multiplicity 2, and then is another one 10. Now of course you know this, that if we would like, we can do this. We got 1 1 0, oops, 0, and then we can have this. Sorry about that. Okay. Then let's write the other values. So we got 1/2, 0 and 1, and then -2, 2 and 1. And if we take the inverse and multiply this by the original matrix, okay, and then take it here, so you have 1 1 10. So this is similar to a diagonal matrix. Okay, now but what we need is that we need these columns to be orthonormal. That is, we need them to be unit vectors. Okay, and we also want them to be orthogonal to each other. So now here you see this vector and this vector, they are orthogonal to each other, and so are this and this. Okay, because of the spectral theorem of the symmetric matrices, okay, that we had referred to before. But these two are not. So what we can do is that we can go ahead and use, remember what you called that, your Gram-Schmidt process, right? Or orthogonalization process. So what we can have is that this is the basis. So these are two linearly independent vectors. So let's take that as our first set, and then do this. For the second one, what we have to do is that we will take its component that's perpendicular to this one. So how do we do that? We will take this vector, okay, take the dot product here with this, all right, and then right here, okay, and then what we are going to do is that we are going to multiply this by this vector here, and what we have gotten is that, see, this vector and this vector, they are orthogonal to each other. And if we would like, so let's make a unit vector along, let's create a unit vector along this one. So what you have is, what will be a unit vector along this? Okay, let me just say it is 1 over square root of 2, because square root of 2 is its magnitude, right? And then we would also like to have a unit vector along this vector, okay, and instead of doing things in my head and making mistake, okay, let me just quickly compute the length or magnitude of this vector. Okay, all right, so you have then this, then next you got this negative sign, okay, and then you have what 1 square, and if you look at it, what do you get? Okay, 3 over 4 square root of 2. Okay, or I'm just going to write it like this just for sake of like simplicity later. So in this case, what we are going to do is we are just going to multiply the components by the reciprocal of this vector. So what do we get is right here we get 2 square root of 2. Downstairs we get times 3. Here also we have 2 square root of 2, and there we got this times 3, right? And then you have again 2 square root of 2 over 3, and which is, after that, let's just reduce it further. So or what we got is, here we have 2, this 2 cancels, and 2 times 3 is 6. We will have same thing here. We got this as 6, right? And just to make sure that we did our calculation correctly, okay, let's verify that. Yes, so the dot product is 1. That means, yeah, this is also a unit vector, and this we are having total confidence in ourselves. So what we got is that we have we get this vector, and then we got this vector right here, and then the third one was what? Let's go back. This, and this is not a unit vector, right? So no problem. See, 4 plus 4 is 8, plus 1 is 9. So here things are easy. Its length is 3. So this is what? This is a set of orthogonal vectors from where? From the eigenvectors, all right, of the given matrix A. So we will go ahead and then just let's create these matrices. Okay, so we got this, then this value, and 0 as our first column, right? Now let's make the other columns quickly. Okay. So here you go. Okay. So then you have negative square root of 2 over 6. Oh no, that was not negative. Okay. Then negative square root of 2 over 6, and then this, and you can see this here, that this type of orthogonal diagonalization, we can do it only for symmetric matrices. Okay, so keeping this, and then we will take the inverse of this. All right, and then what was my original matrix? It's right here, and we will again expect what? We will again expect 1, 1, 10. Remember, 1 is an eigen value of multiplicity 2, and here we go, we got 1, 1, 10. So now let's go for a payoff. Okay, and a payoff of this thing, that is, just using it, and we are going to use it in a real very simple situation. So a payoff is this, that is, say I have a function, just a function, not a linear transformation. Okay, so we are just taking a simple function R2 to R, where this function does this, that say we got right here x1, x2 equals say 3, x1 square, okay, minus 4 x1 x2 plus 3 x2 square. Okay, so we got that, right? Okay, so now this is called a quadratic form. Okay, so here you have a polynomial of degree 2, and you can extend this to quadratic forms from Rn to R, which are functions with values of what polynomials of degree 2, okay, in the variables involved in the domain space. Okay, now we can do this, that we can associate a symmetric matrix to this quadratic form in the following fashion. See this here? The terms of the perfect squares, let's put those in diagonal. Okay, and the coefficient of the product term, okay, that is x1 x2, and if we had more variable like x1 x2 x2 x3 etc etc, we would arrange them in a different way. So what we will do is, let's take this coefficient here and divide it by 2. So what we got now is, we got a symmetric matrix, and this matrix is, this will come out to be pretty handy and useful in the following sense, that if I took the transpose here, took the matrix, okay, and let's just take this here again, and what that will do is that will just go ahead and give us the same functional output. Okay, so here we go, you can see these are identical. Okay, now since it is a symmetric matrix, okay, let's go ahead and orthogonally diagonalize it, and then we will see that how that diagonalization helps us in the display of various level curves of this function. Okay, so here we will go to what, to, let's find the eigenvectors. So we have the eigenvectors as 1 1 and negative 1 1, corresponding to 1 and 5. Okay, and so that will be pretty easy. Here we will divide it by the lengths of the vectors, and lengths are like quite easy here to handle. Okay, and this one becomes what, this one is negative 1 over square root of 2, 1 over square root of 2. And if we do this, that if we go ahead and say diagonalize it, then what we shall have is that we get this, all right, and then, excuse me, get this, right, and we will have the inverse, then we have the matrix, and then we have our orthogonal matrix. Okay, and we got 1 5, our diagonal, the way we wanted. Okay, so if we did this, like, let's look at a level curve of this function of two variables. I'm going to do this instead of x1 x2, just to help this grapher graph this for me. I'm changing it to this, and I mean the same thing. Let's give it a value, say 12, and I could have taken anything I wanted, and if I plot it, you can see that what we got is, we got an ellipse. Okay, and so here is your ellipse. Let me just make it a little bolder so that we can see it better in our picture. Come on. Okay, so it's a tilted ellipse. Now, what will happen is this, that if instead of taking our coordinates with respect to this regular x and y, say we go along this and this, so there will be another set of perpendicular axes, and a vector along this, you can see x and y are the same, so I can graph an axis like this. Okay, y equals x, and for the other one, remember, x and y are negatives of each other. So if I did this, what will happen? See, with the change of these coordinates, my ellipse will come out in a regular shape regarding the equation. What I mean by that is the following. That is, say we go ahead and take a new set of coordinates, call it u1, u2, along those new lines, right? So we have u1, then we have u2, and since we are taking this to make the transformation, all right, what we will have is this quantity will be what? This will have to be x1, x2, right? So here we go, x1 and x2, right? Okay, so notice this, that the value that we have here is what? We just saw that value is what? That value is this value, right? Okay, so if I did this, say we got this here, right? Okay, now we already see who x1, x2 is. That's transpose of this vector, right? Okay, so here we go, we got transpose, and in the middle we have our original associated symmetric matrix, and then we have the vector itself. Okay, so I'm just doing just your basic algebra 1 in your linear algebra, right? Okay, so what we have now is, see, when I take the transpose, what it will do is the positions will reverse. Okay, so I have this, then I got the transpose of this vector, right? Now it's an orthonormal matrix, so what will happen? The transpose and the inverse will be the same in this case, and so we have this now. Now, as I just said, that this will be the same as the inverse of itself. Okay, so no, this will be the same as the inverse of the base matrix, and quickly recall that. Okay, quickly recall that. What was this? This was 1 0 1 5, the diagonal matrix, right? So yeah, this was diagonalized, so a payoff that we get here is this, that is the middle one would be the diagonal matrix. I don't know why I erased that, but anyway, it will not take us long to write that product. Okay, what was that? 1 0 0, oops, 5. Okay, and if you look at its value, all right, what it becomes is u1 square plus 5 u2 square, or I could have taken it as u and v or whatever. Okay, and then this equation that you had taken here now becomes like equation of your regular looking equation of an ellipse, that is, that equals 12. All right, so this is the payoff, and we will continue further with more examples. Let me know if you have any questions. Okay.